Alright, in this video we're going to take a look at an important process in both math and computer science. We're going to look at recursion. Recursion is the process, you look at the definition here, it's the process by which an object is defined in terms of itself. We have a sort of natural intuition to do this sometimes. When we looked at sequences earlier, arithmetic and geometric sequences, often we sort of recognize that the next term was twice the previous one, or the next term was 4 more than the previous one, or something like that. And our natural instinct was to come up with a recursive definition, but in those cases we wanted a direct definition. In this case we do want a recursive definition, and what we're going to look at first is sort of how to follow and compute values using recursive functions. And these two functions happen to be very important mathematical functions that you should be able to recognize once we do this a couple times. But we wanted to sort of just go through the process of a recursive function. So in this case, f of n, right, is a function. You put the number n in, you get a value out. Well, the way that f of n is defined is it's based on f of n minus 1. Okay, so if you want to figure out f of 9, you're going to have to take f of 8 and then add 3. If you want to figure out f of 8, you're going to have to take f of 7 and then add 3. And you're going to basically keep doing this recursively. That's where the recursion comes in, over and over again on a smaller problem until you get down to f of 0 equals 0. Okay, so there's a nice way to sort of set these up on paper so that you can sort of get used to following this process. Okay, in order to figure out f of 4, we're going to have to take f of 3 plus 3. Okay, right? If you let n equal 4, then n minus 1 becomes 3, right? And that's great, except we don't know what f of 3 is, right? So how are we going to figure out f of 3? We're going to apply the definition again. F of 3 is f of 2 plus 3, right? But we're in the same boat. We don't know what f of 2 is. So we're going to figure out f of 2, right, in terms of f of 1, which will be f of 1, right, plus 3. Okay. And then we'll figure out f of 1, which we still don't know what f of 1 is. Right? And the previous one, the one before f of 1, or 1 minus 1 is 0. Okay. Try my hand. My pen's still giving me trouble here, so just bear with me. F of 0 plus 3. Right? And now we're actually in a good place because we know what f of 0 is, right? So we can basically stop once we get down to a value we know. So f of 0 is 0. That means I can put 0 in here, right? And the key is we started working our way down like this, and now we're going to be able to work our way up. We know what 0 plus 3 is 3. Okay, we can now take that 3 and feed it in to f of 1, right? F of 1 is now 3, right? So this becomes over here, right? Let me just clean that up. Let's try this again. This becomes 3 plus 3, which is 6. Okay? Now again, the idea is that that 6 here is going to get put into this f of 2, right? Which will make this 6 plus 3, which is 9. That 9 will get put in here. 9 plus 3 equals 12, right? And that's our final answer. Okay, so the final answer we get for f of 4 is 12, right? So we started, f of 4 needed f of 3, which needed f of 2, which needed f of 1. Once we had f of 0, we could work our way back up to get f of 4. So if you sort of think about these visually like this, it becomes easier to follow. And if you get into programming, or if you've already done some with data structures, this is essentially like a stack, right? F of 4 is waiting for f of 3 to finish. F of 3 is waiting for f of 2 to finish or compute. F of 2 is waiting for f of 1, and so on. So we can sort of think about f of 4 being on the bottom. F of 3 gets put on top of that. F of 2 gets put on top of that. F of 1 gets put on top of that. And then once you can start doing values, you can sort of take them off the stack and do the computations. Okay. Now, if you also notice, take a look at the sequence here, right? We have 3 6, 9, 12, right? What does it mean when you repeatedly add the number 3 over and over again, right? Repeated addition is multiplication. So this recursive definition that we had at the beginning, right? This f of n equals f of n minus 1 plus 3 is really repeated addition of 3, which is going to result in multiplication, right? So we probably could have now seen that 4 times 3 is 12. We could have skipped all this work maybe, right? But this is just following the recursive definition. Using the same logic over here, in this second example, we're going to have repeated multiplication. So you might already know or have a guess as to what the answer is going to be. F of 4 is going to be, right, f of 3 times 3, okay? F of 3 is going to be f of 2 times 3. Right? We don't know what f of 3 is, so we have to compute f of 3. We don't know what f of 2 is, so we have to compute f of 2. Right? F of 2 is f of 1 times 3. We don't know what f of 1 is, so we have to compute f of 1. F of 1 is f of 0 times 3. Now, again, we've sort of finally reached the point where we know something. We know that f of 1 equals 0. Okay? So since f of 1 equals, f of 0, I'm sorry, I read that backwards, f of 0 equals 1, right? This here gets replaced by 1, so we get 1 times 3, or 3. Right, now we're going to follow the same process. We worked our way down until we got a value we can use. Now we're going to work our way up. This 3 takes the place of f of 1. 3 times 3 is 9. This 9 takes the place of f of 2. 9 times 3 is 27. 27 times 3 is 81. Right? So we get the final answer here, f of 4 equals 81. Okay? So we now have recursive definitions for very common mathematical operations, multiplication and exponentiation. Right? Because repeated addition is really what multiplication is, and repeated multiplication is what exponentiation is. So we learn how to define them directly. We also have ways to define them recursively. Most of the time, if you're given a problem to do, it might be just sort of a made-up nonsensical function just to see if you can follow the steps. So you just plug in the previous value, you keep going until you reach sort of your stopping condition, right, where you actually know a value, and then you can sort of work your way back up. Okay? We can also do recursive sequences, right? I sort of mentioned this at the beginning, that we had some experience with this before. It works basically the same way, just instead of using function notation, we're using sequence notation with subscripts. Okay. In this problem here, in this very first one, I want to find a sub 3, so I'm basically telling you that n equals 3. Well, this definition says take 2 times a sub 2, which is the previous one, and then add 1. Okay, well that's great, except we don't know what a sub 2 is. So we'll figure out a sub 2, right, by taking 2a sub 1 and then adding 1. Okay, again, we don't know what a sub 1 is, so we keep going. A sub 1 is 2. Clean this up. I was doing good for a little while, but 2a sub 0 plus 1, right? And now we've gotten to a point that we're in good shape. We know what a sub 0 is 5, right? So this is really 2 times 5 plus 1, or 11. That 11 comes up here into a sub 1, so we have 2 times 11 is 22, plus 1 is 23. And then we can take that and put that in here. 2 times 23 is 46, plus 1 is 47. Okay, so we now know that a sub 3 is 47. Okay, this is not an obvious or familiar function, it's just something we made up here. Okay.